Okay, right, we're going to pick up this morning with torsion, which is covered in clause 6.3 in Eurocode 2 part 1.1. There is, most of the rules are in Eurocode 2.1.1, the general rules and rules for buildings. There are a few modifications made in the Eurocode 2 part 2 for bridges, so they're pretty trivial, and it's really just limited to a statement about how you apply the rules for torsion to box girders. But actually, it doesn't really need saying because it's pretty obvious. So what we're going to cover here is first of all some types of torsion, because the Eurocode makes some clear distinctions between different types of torsion in its clauses. Then we're going to look at how the resistance model to torsion is built up in Eurocode 2. And then we'll look at specifically how you apply the rules to box girder sections and to open sections, such as typical M beams, pre-stressed beams. We'll mention just very briefly about torsion in slabs, but only really to say that these rules don't cover torsion in slabs. You have to use something else. Either wood armour, which strictly isn't covered anymore, or something called the membrane and shell rules have to be used. So if we just first of all look at types of torsion. I think a bit like we were saying yesterday for shear, it's in the past torsion hasn't really governed the section dimensions of members, and that's going to be the case again in the Eurocodes. So the normal procedure is basically to design for shear and bending, and then check for torsion in just the same way as we've used to do. The Eurocode talks about two types of torsion. It talks about equilibrium torsion and compatibility torsion, and they're specifically covered in the two clauses in the lower bullet here, and they're important because one of those types of torsion you can neglect at the ultimate limit state and the other you can't. So first of all, by equilibrium torsion, the Eurocode is talking about a situation essentially like the one up on the screen. So if I apply an offset load to a cantilevering beam like this, then the only means of actually carrying that load is to have a torsional stiffness and strength of that beam. If it doesn't have torsional stiffness and strength, it will obviously just twist and the load will fall off. So since that's necessary for equilibrium, that's what the Eurocode refers to as equilibrium torsion. And that also applies to things like curved beams, where as you move around the curve, a bending moment turns into a torsion. You have to have that torsional strength and stiffness for stability of the curved beam. It's not just enough to have bending strength. So then the Eurocode also talks about compatibility torsion, and as it sounds, these are torsions which arise just purely because of rotations in the system and the stiffness against or resisting those rotations. And a good example of a compatibility torsion is again this sort of grid frame system, where if we do an elastic analysis and the beams all have some torsional stiffness and rigid connections, and we put a load on there, we'll get a bending moment diagram in the beam with a fixed end, well not fixed end, but we'll get a hogging moment at its joint to the other beam. And that's arising purely because this beam here has some torsional stiffness. But if we were to do the analysis again, and this time set the torsional stiffness for the other beam to 0, then we'd end up with 0 bending moment at the end of the beam, because the beam would end up being simply supported on the other beam, and the beam would just twist without actually being able to provide any bending resistance. So that's an example of compatibility torsion, and the Eurocode basically says as long as you have a system that remains in equilibrium, then this sort of torsional effect you can shed basically by being clever with the section properties. If I go back to doing, I'll jump back to that particular analysis, what the Eurocode is not saying is that I can just ignore the fixed end moment without actually looking at the effects of increasing the sagging moment. But it is saying that you can vary the section properties to shed these sort of compatibility effects, providing you have equilibrium at the end of it. So in terms of resistance to torsion, the Eurocode, again, it refers to different mechanisms, and you'll see references to synvenant torsion and circulatory torsion. And some textbooks basically call both of these systems synth-bend torsion. So the Eurocode is making a distinction really just between open sections and hollow sections. So when it says synth-bend torsion, it's really referring to a closed flow of shear around an open section, such as the eye girder on the left. And when it's talking about circulatory torsion, it's really talking about a flow around a hollow box type section. We also have references to warping torsion. There's not really a lot of detail on how to cover warping torsion, but it does make reference to warping torsion, which previously BS500 didn't even really recognise. And essentially, Sorry. I'm sure that will go away in a minute. Essentially, warping torsion really arises where there's a closed, a short section of beam between restraints, and when you twist the beam, rather than the torsion being taken in a closed flow of shear around the perimeter of the beam, the torsion is carried in opposing bending of the flanges. And for short sections of beam, that can be quite an efficient mechanism for carrying the torsion. For long sections, the flanges are obviously relatively flexible in bending between the restraints, and they're not stiff enough to pick up the torsional load, and then the torsional load does in fact go into the circulatory torsion or the synth-bend torsion mechanism. But what the Eurocode says with warping torsion and the other types of torsion is that, again, as long as you have equilibrium, then you can carry the torsion by either of those means. It doesn't have to be the exact elastic distribution, but as long as the torsion can be carried by a summation of the mechanisms of the flanges bending sideways and the closed flow of torsion around the section, then that's a legitimate design. There's one clause, clause 6.3.3, paragraph 2, which basically gives you some hints if you actually want to determine the true distribution of torsion between the warping mechanism and between the synth-bend shear flow mechanism. Then it says that you can either set up something like a shell FE model, or you can do a simplified space grillage type model. And I won't go through it, but the example up there is really just trying to demonstrate how you might go about setting up a 3D representation of a beam. That if you twist it as part of a grillage, it will pick up both the transverse bending that goes on in the flanges and also the synth-bend torsion that goes on in the eye section as a whole. So now we come on to how the actual resistance mechanism works in Eurocode 2. And the first thing to note really is, regardless of the section, whether it's solid or whether it's truly hollow, the idealization in the Eurocode is always to come back to pretending the section is a hollow section. So this general cross-section that we've got here is not a hollow section, it's supposed to be a solid section. But what the Eurocode says is if I want to work out the torsional resistance of this section, I need to define an arbitrary outer wall thickness. So the wall thickness that we've defined, and the definition of the wall thickness as we go around is TF here, and each part of the wall, each side of the wall can be a different thickness. It doesn't have to be the same thickness all the way around. But having defined this outer wall thickness, then it's that outer area which resists the torsion, and the inner core area doesn't participate in the torsion at all. Some other definitions really just listed out here. AK we need, that's the centre area enclosed by the centerline perimeter of the effective wall thickness. Tau is the shear stress in each of the walls. A is the area of the whole cross-section basically. U is the outer circumference of the whole cross-section. And then Z here is basically the side length of each of the walls. And there's plenty of choice here again for the designer, because the wall thickness is basically up to you to decide. We'll talk about that a bit more, about how you go about choosing that. So first of all, the Eurocode basically says if you've got absolutely no idea whatsoever as to what thickness to make the wall, it recommends trying a wall thickness of A divided by U, where A is the cross-sectional area and U is the outer perimeter. And there's no particular logic for that, other than if you go for a wall thickness of that size, it gets a reasonable balance between minimising the reinforcement and not having concrete crushing as a limiting factor. But the effective thickness is yours to choose, so this is just a starting point, and you don't have to even start with that as an iteration. There's one caveat on wall thickness, and that is that you cannot make it less than twice the distance from the edge of the section to the centre of the longitudinal reinforcement. And the reason for that is if you go for a very, very thin effective strip, then it means that the centre of your shear flow actually lies then outside the reinforcement. And the way the model is going to work is we're going to design basically each strip as we do for shear, as a beam for shear, so using the truss model. And basically if your truss is lying outside the reinforcement, well, it ain't going to work because the cover will just come off. So that's an overarching requirement, that you mustn't have an effective thickness that's smaller than that. You might wonder why would you ever think about choosing a very, very small thickness. Well, as you'll see from the equations in a minute, the smaller you make the wall thickness, the bigger basically is the torsional lever arm. And the bigger you make the torsional lever arm, the smaller the requirement that you have for the reinforcement. But similarly, the smaller you make the effective thickness, the less concrete there is to actually resist crushing in shear. So if you make it too thin, then you'll exceed the maximum allowable shear stress. So it becomes a balancing act again. We have to get the thickness right to basically suit our particular needs. The way the torsional formula is derived in the Eurocode is basically, first of all, just to start with hollow-walled theory, which is the top equation. So we know from hollow-walled theory that the applied torsion is equal to twice the area enclosed by the middle perimeter of the hollow wall times the shear flow, tau times effective thickness. And we also know that the shear in each of the walls, V, is basically equal to the shear flow, tau times T, times the length of the wall Z. And if we equate those two together, we get an expression for the shear in each wall, which is equal to the shear force divided by twice the enclosed area times the lever arm. And we can then equate that shear force to the shear resistance of a little beam made up of the side wall, using the formula we had yesterday for shear, which is done down at the bottom. And equating those two together basically gives you these two formulae for the transverse reinforcement as a function of the area we need to provide per unit length along the beam, and also the longitudinal reinforcement that we need to provide around the section as an area per millimetre or per unit length around the perimeter. We can also look at what the shear stresses in each wall and set the limiting shear stress to the limiting shear stress that we're allowed for shear, again using the work in clause 6.2 of the Eurocode on shear. And that then basically gives us a maximum allowable torsion, a bit like the maximum allowable shear, VRD max. It gives us a TRD max, which is the maximum shear torsion we can apply to the cross-section, irrespective of what reinforcement we've put in it before the concrete will crush. So those are basically the three formula that you need to use. What you'll see is that the transverse reinforcement equation has again a cot theta in it, and theta is again a truss angle. And the rules of selecting the truss angle for torsion are the same as they are for shear. So we can vary theta from 45 degrees at its steepest to 21.8 degrees at its flattest. And to make life easy, or indeed make life possible, we should use the same truss angle for the shear design and the torsion design. So if you've got a load combination that has shear and torsion in it, you need to use the same theta angle when you're working out the reinforcement requirements for shear and torsion. If you have another load case, you can obviously then have a different theta angle, but you should use the same one for shear and torsion, otherwise it becomes very difficult to work out how the stress fields will add together. And when we change the theta angle, we have the same effect as we have for shear. So for the transverse reinforcement, you'll see cot theta is on the bottom. So that means if we go for 45 degrees, then cot theta is 1. If we go for 21.8 degrees, then cot theta is 2.5, and therefore we'll end up with 2.5 times less torsional reinforcement if we go for the flat truss angle. For the longitudinal reinforcement, then cot theta is on the top of the equation, and so the reverse applies. So if we go for 45 degrees, we have a multiplier of 1, but if we go for the flat truss angle, we will end up providing 2.5 times more longitudinal reinforcement distributed around the perimeter. So for torsion, you've got lots of things to juggle. You've got the truss angle that you can play with, but you've also got the wall thickness as well that you can play with. And I mentioned earlier that the smaller you make the wall thickness, the more efficient it becomes for reinforcement. Well, you can sort of see that in these two equations again, because as I make the wall thickness smaller, the area enclosed by the mid-plane of the wall, AK, will also get bigger. And for both the transverse reinforcement and the longitudinal reinforcement, you can see that AK is on the bottom of the equation. So the bigger I make AK, the less reinforcement I get in both directions. But the reverse is true when you look at concrete crushing, because the smaller you make the effective wall thickness, the more critical concrete crushing will become. There are some practical problems, and I'll illustrate this when I walk through an example at the end, but there are some practical problems with that definition of effective wall thickness not being allowed to be smaller than twice the distance to the centre of the longitudinal bars. Because sometimes, if you've got very thin webs, like we have with some of our standard pre-tension beams, you'll find that twice the distance to the centre line of the longitudinal bar is actually more than half the width of the section. So we end up with a wall thickness, a minimum wall thickness, which is more than half the actual physical thickness of the wall. So the question is, what do you do in that situation? It arises largely because the drafters of the Eurocode didn't imagine that we'd be trying to apply this torsional formula to small beams like M-beams. In fact, I had a discussion with the project convener for Eurocode 2 about it, and he said, well, surely when you analyse your decks with these sort of M-beams, pre-tension beams, the torsions are so small that you just neglect them. And I said, well, we can't neglect them. You're right, they are very, very small, but then the resistance to torsion is also very, very small. And so when you apply them, there's still a significant effect. So it wasn't intended really to ever apply it to something as small as this. And what you could do is come back actually to where we started with the compatibility torsion and just actually select your torsional stiffnesses of your M-beams to be very small, such that the torsions are indeed very small. And that was the way that most of our European friends are envisaging you do these decks, and not the way that we do them by actually putting the torsional stiffness in and then trying to design for that torsion. So that's what arises. But given that a problem exists and you're trying to design something like this for a torsion, what do you do? And the Eurocode doesn't tell you what to do, as I say, because it hasn't envisaged that this is going to happen. What I recommend that we do is we have to change the assumption for T effective depending on which check you're doing. So when we're designing the reinforcement and we're applying, let me just jump back, we're applying these top two equations, the equation of a transverse reinforcement or longitudinal reinforcement. When we set the wall thickness, the effective thickness, we should use 2 times the cover to the longitudinal bars, even though that gives us a nonsense in terms of physical wall thickness, because we'll be using an effective thickness that's bigger than the wall. But we have to do that to get the lever arm for the reinforcement in the right place. Basically what's happening here is this hollow wall beam theory is breaking down, because the wall thickness is, by definition in that analogy, it's supposed to be a small percentage of the section dimensions, whereas here it's becoming bigger than the section dimensions. So to fudge it, to get it right, we have to just go with twice the cover, even though it creates a physical nonsense. When we're checking concrete crushing, so we come back to TRD max here, then we will get a complete nonsense if we put an effective wall thickness into that equation, which is bigger than the physical wall thickness, because we will have basically too much concrete there and too much resistance. So when we check TRD max, then we have to use an effective thickness which is limited to the physical wall thickness, which is basically half the thickness of the beam. And I'm not going to go through this next slide, but what this is, because we haven't really got time, but what this is trying to do is explain why hollow wall beam theory breaks down in this situation, and the code doesn't allow you to do it. But really, what we should have done to avoid this problem is build up the cross-section resistance by integrating up a whole series of thin-walled sections and adding up the results together. And if we do that, then we actually get a different formula comes out for TRD max, which actually makes more sense than the one in the Eurocode. So when you've got combinations of shear and torsion, I mentioned earlier on one of the most important things is to make sure that we use the same truss angle. But we've also got to be able to add together the effects from shear and torsion once we've derived them using the same truss angle. And what the Eurocode says is if you have a box girder, then you've got a choice really of what you do. You can either add the shear from torsion to directly in each web directly to the vertical shear, and then just design that web for shear. Or alternatively, you can do the design separately. You can do a design for torsion, do a design for shear, and then add the requirements together using a linear equation. So we just check that the torsion divided by the limiting torsion plus the shear divided by the limiting shear is less than 1 when we're looking at maximum shear stresses. And when we're looking at reinforcement, we obviously just simply add the reinforcement required from torsion together. If we're looking at open sections, then what we have to do is very similar to what we used to have to do in BS5 400. So if we've got something like this, which is again a pre-tensioned beam with a made composite with a deck slab, then we have to break down the section into a series of component rectangles. It's coming from. So the rules for doing that, we're not free just to split it up in any way that we like. What the code tells us to do is that we should split the section up in such a way that it maximizes the total torsional stiffness that we derive. So in this particular case, this is actually the right answer. We could have split it up by having one rectangle over the full vertical height, perhaps, and then a series of sort of stubby rectangles sitting out from the vertical piece. Well, if we do that and we add up the stiffness that we've got, then we'll end up with a lower overall torsional stiffness than we have with this particular setup. So that's the one we're supposed to go for. And that's actually no different, again, from BS5 400. I mean, BS5 400 didn't specifically say to maximise the torsional stiffness, but what it did say was it said that you basically should divide it up into such a way that you maximised effectively B max times the summation of B max times B min cubed for each of the components. But that was only really saying the same thing. So, I mean, in the notes you've got just some simple formulae for the torsional stiffness of various different rectangles with different aspect ratios. And I mean, you can see from the table or from the formula that if you go to a very, very wide, thin rectangle, you get back to the classic torsional value of 1/3 BT cubed. And if you've got a square rectangle, then you're in the other opposite corner of the box over here, and you've basically got 0.14 BT cubed. So we can use these formally just to work out the torsional stiffness of each of the component parts, and we just need to check that the total is the maximum. Once we've done that, and we've done our global analysis with that section property in there, then we'll obviously get a torsion in the overall section, and we then have to design that section for the torsion. And what the Eurocode then says is that you have to subdivide the torsion that you've calculated back into the component rectangles, and you do that in proportion to how much they've contributed to the overall torsional stiffness, which is again pretty much what BS5 400 said, only rather than saying torsional stiffness explicitly, it said divide it up in terms of its how much it contributed to BT cubed, basically. So that's it really for torsion of beams. The most important thing to note is that clause 6.3 is only covering torsion in beams. So if you've got torsion in slabs, that's not the place to be. You need to do something else. I mean, historically in the UK, we've covered torsion in slabs using wooden armour. And I think there's no real reason why you can't carry on using wood armour. In fact, the PD that's come out with recommendations for how to use Eurocode 2 Part 2, it stops short of saying go ahead and use wood armour, but it kind of makes some suggestions that it would still be all right to use it. The reason it doesn't give it a ringing endorsement is because the Eurocode has a section on what it calls shell models. And the intention is that we should do our design using this sort of shell type analogy. So if we've got a general stress field, such as the one shown here, then the intention is that you actually split this element into a sandwich. So we have two outer layers and then an inner layer. And basically, for things like bending, we distribute the bending moment as a push-pull force in the two layers. A torsion will be distributed as two opposing shears in the two layers. And then there's a set of equations that we use to work from just the in-plane forces in each of the layers to turn them into reinforcements. And what you'll find is we get very, very similar answers to wood armour doing that. But this sandwich model introduces one more check which wood armour doesn't have. And that's an explicit check on the compression field within the layers. So this is a bit like the equivalent of a VRD max check for shear. We have an inclined, we'll have an inclined compression field as a result of these in-plane forces, and that theoretically needs to be checked out. Wood armour didn't check that, and therefore this is why the Eurocode doesn't explicitly sort of say use wood armour, and this is why the PD doesn't explicitly go as far as say wood armour will always be okay, because it actually omits this check of the compression field. Having said that, it hasn't been a problem in reality, and therefore there's no particular reason why we're going to suffer from problems in it in the future. I'm not going to go through any of this now. There is a session on sort of sandwich models later on, which we may or may not have time to do. But this is really just trying to describe what I've said is a way of turning the forces in a general sort of in and outer plane stress field into simply just in-plane forces, and then we can derive the reinforcements from just a set of equations for the in-plane forces. And it gets quite complicated when you've got skew reinforcement.
Is this convention to be done through computer?
It's a very, very good question, this. I mean, if you look at the equation we have on the previous slides here are actually in the Eurocode. So as long as you've got orthogonal reinforcement, you're fine. You can work out your reinforcement. It doesn't cover skew reinforcement because the rules were primarily drafted for analysing complicated structures, like, again, sort of weird-shaped box girders, where the reinforcement was still predominantly orthogonal, even though the overall shape was complex. And it wasn't so much drafted for thinking about probably what we're thinking about, sort of slabs, skew slabs, where the reinforcement is quite likely to be skewed. So you can follow the same derivation of these equations, and you can produce these equations there, which are basically in the Thomas Telford guide, but not in the code, because we just followed the same logic and produced these equations. But yeah, you're right. You basically need something like a spreadsheet or a computer program to do it. I mean, with wood armour, we've typically relied on software manufacturers to have that implemented, but we have got a program. I think Tony Smith wrote a program that basically looked at moment fields, general moment fields, and applied the sort of moment field equations and derived reinforcements. But you have to kind of do that on every single point in your model, so it's not very practical. And this is no more practical because, again, it has to be applied to every single point in your model to derive what the reinforcement is. So if you're doing a global analysis, you really want something in the computer that does this for you. But to my knowledge, nobody has done that yet. In fact, it's similar to the conversation we had yesterday. I had a few meetings with the people at sort of Sam Leap. First of all, just for them to try and get their head around what a sandwich model actually is, and then how they might go about implementing it. And at the moment, they're not doing anything. They're kind of hanging their hat on the fact that the PD basically still thinks wood armour is all right, so they're just hoping that engineers will carry on using wood armour. But strictly speaking, we shouldn't really be doing that. We should move across to the sandwich model, but I don't think it has any real practical consequences, as other than omitting that compression field check. So, I mean, just to finish with a couple of quick examples to sort of walk through. If we've got a box girder, things are pretty simple. So this example just looks at designing the reinforcement that you need in a web purely for torsion, and the calculation would then be repeated for the flanges as well. So if we've got a hollow box like this one here that's actually got a physical wall thickness already, then the logical thing to do is, when you're choosing T effective to work out the torsion resistance, is just to choose the full effective thickness of the wall. It would be a bit perverse not to do that. So in this particular example here, the wall thickness is well defined already, and it's 500 millimeters all the way around. So that allows us to calculate the value of AK, the enclosed perimeter of that cross section, which comes out as 16.9 times 10 to the 6 millimeters squared. So then we can just go straight into calculating what the torsional requirements are for shear links. In the particular example, we've got a total torque of 10 meganewton meters acting. So from the first equation in the code, we can get the transverse reinforcement requirement, and the only thing we need to decide upon there is what truss angle we're going to use. Now, as I said earlier on, if we want to minimize the vertical reinforcement, then we'd go for a flat angle, but that will result in more longitudinal reinforcement, and it's less efficient for also for the maximum shear stress. Going for a steeper angle is the most efficient for the maximum shear stress requirement. So in this particular example, for no really good reason, theta was just set to 45 degrees, really following kind of the old BS500 practice, on the basis that that will actually result in the thinnest web if we want to refine the thickness of the web. So that gives us a torsion requirement vertically of 0.68 millimeters squared per millimeter to be provided by both the shear links in the web. And if we go for a 45-degree truss angle, then that actually means that the longitudinal reinforcement will be an equal amount to the transverse reinforcement. So we can see that in the second equation here, we get the same requirement for longitudinal reinforcement distributed around the cross section. And then the last thing we need to do is just check that the concrete outline itself is okay to carry 10 meganewton meters. So we use the equation for TRD max. Again, the effective wall thickness is the full thickness of 500 millimeters. We've already got the enclosed perimeter area, and theta again we need to choose as 45 degrees for compatibility. And when we do that, we get a TRD max value comes out of as 114 meganewton meters. So for this particular load case, we're only using up 9% of the concrete resistance for torsion, and therefore when we come to do the shear design, we can have up to 91% of VRD max in the vertical shear design. So that's pretty straightforward, where you've got a physical wall thickness already provided to you. So the second example is an M-beam example, pre-stressed beam made composite. This time we've got a very much smaller torque of 40 kilonewton meters, which we've obtained from a grillage model. And we basically need to design this cross-section now for that share of the 40 kilonewton meters. So the first thing we would have to do is to split the thing up into rectangles. We would have needed to do that to work out the torsional stiffness before we did the grillage analysis. And so you can see the way the section's been split up, and then the calculation here is basically working out what the torsional stiffness of the deck slab, the top flange, the web and the bottom flange actually are, and hence what the total torsional inertia is of the whole cross-section. So having got those individual torsional stiffnesses, we then work out what the share of torsion in each of those elements is on the basis of the share of the torsional stiffness that it contributed. So for example, the deck slab contributed 6.144 out of 39.67, and therefore the torque that's attributed to the deck slab is 6.144 over 39.67 times 40. That's the total torque, and that gives us a torque of 6.2 in the deck slab. And the top flange has 12.8, the web has 3.2, and the bottom flange picks up 17.7. So then we've got to actually design each of those components for those torsions. The top slab we don't treat using these beam rules, as I mentioned, because the top slab is part of the two-directional slab. So we just take the torsion that's in that and we go away and add that into the general moment field that we've got from the global analysis, and then we use wood armour, or we use the sandwich model to work out what reinforcement we need in the top slab. So that's part of a separate calculation. We then have to look at the individual parts of the pre-stressed beam. So we start off with the top flange there, which is 400 mm by 250 millimeters, and as a first stab for the effective thickness of that top rectangle, we could just go for the Eurocode suggestion of setting it equal to the cross-sectional area divided by the perimeter area. And if we do that, we get an effective thickness of 77 millimeters. But we then come back to the fact that we can't actually make the wall thickness less than twice the distance to the longitudinal reinforcement, which you can see is 2 times 45 millimeters. So we actually can't, we're not allowed to make the wall thickness less than 90 millimeters. So we can't use the suggested value of A over U because it's too small. We have to go for 90 millimeters. So we've now got a wall thickness of 90 millimeters. We can calculate the perimeter area, AQ, of the centre line of that effective wall thickness. And then, having got that, we've got all the bits that we need to work out the transverse and the longitudinal reinforcement again from the standard formula. And the only thing we've got to decide again now is what truss angle to go for. And once again, it's a bit boring in this example. It's just been set as 45 degrees, so we get the same reinforcement requirement in both directions. But it needn't have been set that way. So that means we get basically reinforcement requirement of 0.297 millimeters squared per millimeter in both directions. So that basically equates to 8 mil diameter closed links at 100 mil centres. We've then got to check just to make sure that we're not going to crush that rectangle with the torsion, so we need to check TRD max. And the maximum value of TRD max that we get out is 60 kilonewton meters, which is quite a bit greater than 12.8 kilonewton meters, which is the torsion in that rectangle. So we're effectively stressing that to 21% of its maximum shear stress requirement, which means that the remainder of that is then spare for vertical shear. 79% of VRD max is spare for vertical shear. When we come to the web, we basically have to repeat that same calculation, but we fall foul of this problem where the effective thickness is going to be more than the wall thickness, or more than half the wall thickness. So if we follow through the Eurocode, we might again try the effective wall thickness to be A over U. That comes out as 54 millimeters, which is again smaller than twice the distance to the longitudinal reinforcement of 90 mil, so we can't have that. We need to be starting with 90 millimeters. And so when we come to do the design for the transverse reinforcement and the longitudinal reinforcement, even though making a wall thickness of 90 millimeters is a physical nonsense, we still have to use that to get the lever arm for the torsional flow in the right place. So we calculate an AK based on the section dimensions and a wall thickness of 90 millimeters. And that gives us, again, if we choose the same truss angle theta of 45 degrees in both directions, we end up with the same reinforcement in both directions. Again, we have to check also that we're not going to crush the web in torsion, so we have to check TRD max. But this time, as I mentioned earlier, it's not going to be realistic or safe to have a wall thickness which is actually physically greater than the physical wall thickness. So when we do the check on TRD max, we have to recalculate the perimeter area, setting the effective thickness equal to the actual physical half thickness of the wall of 80 millimeters. Otherwise, we'll have too much concrete present in the calculation. So in this particular case, you'll see we've got two AKs. We've got one calculated for reinforcement and one calculated for shear stress. And when we calculate what TRD max is, we've got 21.9 kilonewton meters allowed, we've got an applied torsion of 3.2 kilonewton meters. So we're basically stressing the web to 15% in torsion, which is leaving us 85% for shear design.